Hey there, Xtorians! Today we're going to be learning how to create a functioning clock, like this one. Oops, let me get this one set up real quick. There we go. That's more like it. Today we're going to be learning a little bit more advanced materials for Rooms 2.0, including the state machine. Today we're going to be using something called a compound object, which is basically a container mixed with circuitry. So, this can be used in a variety of different ways to create more complex objects within your room. Go ahead and start by designing your clock. First up, design your clock face. Make sure to remember to design the hour, minute, and second hands, or whichever hands you wish to include. You also need to know where the exact center of your clock face is, so that we can place the rotators there. Make sure to mark it. Now that you've designed your clock face and clock hands, select each of them at the exact same time. When you have done that, you will find a Baymax face. Click on that, and then click Group. This creates a container. We are now going to want to edit into the container itself. You'll know that you've done this when the rest of the world becomes white. When you are in the container, you are going to want to spawn rotators, one for each clock hand that you're going to be using. To connect the clock hand to the rotator, we are going to wire the clock hand to the gold part of the rotator. Then we're going to move the clock hand to be on top of the rotator, where the bottom of the clock hand is on the center of the top of the rotator. And it's going to be orientated with the arrow in the rotator. When you wire something to the rotator, it will create another container. So in order to move the clock hand to the center of the rotator, you're going to need to edit into this container as well. Now that we have all those connected up, I would recommend renaming each of the rotators to be what hand you want that hand to be. Now that they are each named, we can move on to all the circuitry part of this, and the logic behind a clock. We are going to start with the second hand. What we wanted to do is every single second, we want it to tick and rotate. In order to keep track of that, we're going to do what most cookers do. Use a variable and an add chip. For this instance, we're going to be using a float variable. Rename the float variable and crisscross its output and input with the add chips. We will also sync the variable to make sure that it plays the same for everyone. We are going to be adding one tick every second, so make sure to configure that properly. Spawn in an if and equals chip. For the second hand, this is technically not necessary, but it will make more sense for the minute and hour hands. Connect the output of the equals to the input of the if chip, and the output of the tick to the input of the if. We are also going to connect the output of the float variable to the input of the equals chip, and change the equals to, say, 1. Now that we know how to count each tick, and how to check which tick that we're on, we need to figure out what each tick does. What we want each tick to do is set the rotation of the rotator. So we need a rotator set rotation, and go ahead and connect the then output of the if chip to the input of the rotator set rotation. The target of this chip will be the second rotator, or the second hand rotator. And now we need to figure out what rotation to set the rotator at. If we set the rotation to a specific number, every single second it will only change to this number. Thus, the second hand will not move after the first tick. So we need to find a way to update this each time that it ticks. In order to do this, we're going to use a rotator get rotation. When we wire the rotator into the rotator get rotation chip, we will know which rotational degree we are on. But if we connect it straight into the rotator set rotation, we're just going to set it to the same one that it currently is on. So we're going to need another add chip to add a specific number of degrees per rotation. Wire the rotator get rotation into the add chip, and the add chip into the rotator set rotation. Now we need to figure out how many rotations can the second hand do. Well, we know that there are 360 degrees within a circle, and there are 60 seconds in a minute. So we need to figure out how many degrees to turn the rotator every single second in order for the hand to make a full rotation in just 60 ticks. If you remember fractions in middle or high school, you'll remember how to do this. We're going to put 360 degrees on one side and 60 seconds on the other side. Now we need to figure out how many degrees it needs to change per second. So we need the second to be 1. To do that, we're going to divide 60 by 60 in order to become 1. What we do on the bottom needs to be done on the top. Therefore, 360 divided by 60 equals 6. So the number of degrees that we need is 6. The last step is to reset the tick counter every time the clock hand rotates. So we're going to get a delay chip, and we're going to clone the tick counter so that we can reset the tick counter. We're going to be using a delay chip to prevent both of the float variables from executing at the exact same time, causing any errors. So go ahead and connect the output of the rotator set rotation into the input of the delay, and after delay, go into the second float variable. We are only going to be changing the delay to 0.1. Now that we have all of this figured out, we can go ahead and clone it into the minute hand, as all of these hands work the same. So make sure to click everything except for the rotator itself, and clone it downwards. Now grab that minute rotator and add it to the mix. We're going to be connecting it the exact same way that the second hand rotator was connected. That means connect it to each of the rotator get rotations. We will also need a new name for our float variables, as this one is the same as the second hand. Now that both of these float variables have been changed to talk instead of tick, we need to double check our work. Remember the if and equals chips that I said earlier? This is where it makes sense. Because there are 60 seconds in 1 minute, we need to change this equals to 60. Now that the equals chip is set to 60, every 60 seconds, the minute hand rotator will rotate once. There are 60 minutes in 1 hour, so this add chip can say the same. Now we need to connect the minute hand to the second hand, so let's do that. Another reason to use the delay chip is so that when the rotator sets its rotation, we can use the run output and run it into the input of the next hand's counter. This will allow every time that the previous hand rotates, it starts the counter on the next hand. When that second hand counter hits its limit or requirement, it will then rotate itself and reset itself to start counting for the next time that it will rotate. We will be repeating the process for the hour hand as well. Get the hour hand rotator in there and connect it the same exact way that we connected the minute hand rotator. With the hour hand rotator connected and the float variable renamed, we're going to connect the input of the float variable into the run output of the previous delay chip. Make sure to rename both float variables and don't forget that part. Our hour hand counter will count up to 60 minutes. This is correct. However, our hour hand rotation null degree is going to be more than 6, because there's less than 60 hours in one full rotation on a clock. So we're going to need to do a little bit more math. Just like what we did earlier, we're going to take the number of degrees and the number of minutes, or in this case, hours, that we need for this rotation of the clock. A clock has 360 degrees, and there are 12 hours that can be found on a clock. So 360 over 12. We need to make the 12 0. So we're going to divide both sides by 12, and that's going to get us 30 over 1, which means that the number of degrees we need our hour hand to move is 30 degrees. Make sure to update that add chip to say 30, so that the rotator for the hour hand will rotate 30 degrees every time that the minute hand completes a full cycle of 60. Now we need a way to start and stop these circuits. We're going to do that with an event receiver, but we're really going to need 2 of them. We will define them later, but for now, all we need to do is wire the first event receiver to the first float variable chip. The second one will also be defined later, but it needs to be wired into a sequence chip with 6 outputs. We are going to need 3 rotator set rotate chips, 1 for each hand. You can just clone these. Now wire 1 sequence chip output into each of these rotator set rotate chips. Wire the remainder of the sequence outputs into the respective 0 float integers. Lastly, wire the targets for each of the rotator set rotates to their respective rotators. This gives us the ability to reset the clock hands. We're now going to create a state machine to toggle on and off the clock when needed. That way it can always be running, or you can reset it and not have it run at all. But before we do that, we're going to make 5 event definitions. These are the event definitions that I will be using. All you have to do to create an event definition is to spawn in an event definition and then change the name. Don't forget to press submit. These event definitions are self-explanatory. Each one will be doing exactly what the name implies. The first one is tick, meaning that it will be the constant tick that runs our clock. Clock on will be turning on the clock, or it will be doing things that need to be done in order for the clock to be turned on in the first place. Clock out will be turning off the clock. Reset clock will be resetting the clock hands. And set clock will be turning the clock to the user's time zone. Setting these aside for a moment, let's get into the state machine. You are going to need to edit into the state machine, not configure. And you're going to see a state active. We're going to clone this, and then you will see a state inactive. A state machine allows us to create different states that we want to be run at different times, and under certain circumstances. We're going to start in state active, and then we need to create a way to go into state inactive, or state number 2. So let's go ahead and edit into the state active. Here we see go to state and state undefined. We can configure this to state 2, or the current inactive state. Now we need a way to activate it and send our current state to the second state. So let's get an event receiver. This event receiver can be configured to clock on. Wire clock on into go to state. Now when clock on receives a signal, it will take us to state 2. Let's edit out of this state and edit into the state inactive, or state number 2. Now that we're here, we might as well configure the state constant to be the first state. That way, both states will send us to the other. For the second state, we're going to need 2 event receivers. The first one can be configured to clock out. This is so that when the clock turns off, it will go into the limbo state, or the state that's not doing anything. This state will be doing something. We're going to need an event sender. This event receiver can be configured to update 1 Hz. This will be the constant tick, or 1 beat per second. The event sender will be configured to tick. Connect the 1 Hz event receiver to the tick event sender, and that is all we need to do within the state machine. Go ahead and configure these 2 event receivers with their respective events. The one connecting straight into the hands is going to be the tick event receiver, and the other event receiver will be reset clock. We can now set all of these circuits off to the side as we focus on setting the clock to the player's time zone. We're going to start off with a time get universal seconds and a player get time zone, and an add chip. We're going to put both of those outputs into the add chip. What we're going to do with that add chip is we're going to get the formatted time, but we're going to need 3 of these. Each of the formatted time chips will need to be changed to be just HH, MM, and SS, meaning hour, minute, and second. Now that they are all formatted properly with HH, MM, and SS, connect each of them to the add chip. This will result with the hours, the minutes, and the seconds of the person's time zone. So yes, it is nearly 10 o'clock for me. Because there is no string to float chip, we're going to be using the parse float for each of these. For the second and minute hands, all we need to do now is multiply. We're going to be multiplying by the degrees by which the clock hands will need to turn. So for each of these, it will only be 6. Because the hours run on military time and are greater than 12, simply multiplying it by 30 will sort of mess up our clock. So in that case, we're going to use a greater than chip. We're going to be checking to see if the parse float for the hours is greater than 12. To be able to do something with that greater than chip, we're going to need an if chip. Let's wire the output of the greater than chip to the input of the if chip. That way we can control what happens if the hour is greater than 12 or less than 12. Let's now create another float variable. Let's rename this float variable and make it synced, just like the others. We're also going to need 2 of these. One for the if hour is greater than 12, and one for if hour is less than 12. Let's wire both of these to the parse float for the hour. The first one will be what happens when it is over 12, and the second one will be what happens when it is under 12. When the hour is underneath 12 hours, it should just be multiplied by 30. If the hour is above 12 hours, it will need to be subtracted by 12. Only then can it then be multiplied by 30. So, where do all these multiplications lead to? They lead to rotator set rotation. We're going to need 4 of them. 1 for the seconds, 1 for the minutes, and 2 for the hours. Make sure to connect each of these targets to the proper rotator. Now we need a way of executing each of these. We're going to start with an event receiver. Configure this event receiver to set clock. Next, we'll need a sequence chip with 3 outputs. Grab a delay chip as well and place it just about right here. We'll actually need 2 more delay chips. 1 here and 1 here. Each of the delays will have 0.1. The event receiver will go into the sequence chip. Number 1 will go into the delay. 2 and 3 will go into the minute and second rotators. The after delay will go into the if chip, and both float variables will go into their respective delays. The after delays for both of these will go into their respective rotator. If you want the clock to turn on immediately after you join the room for the first time, add an event receiver toggled to room loaded. Then simply wire that into the sequence chip along with the set clock event receiver. The final step is to create an event sender. You can connect this to either the minute or the second rotators. Configure this to clock on. Now, because of this, the clock will automatically start once you set it, so you don't have to worry about resetting it every few minutes. We're going to need our counters for both our minute and hour hands. Run the number of seconds that it has been into the minute counter, and the number of minutes into the hour counter. Then move both counters to the end and connect it to either the minute or the second rotators. This will allow your clock to pick up from where it's supposed to. Otherwise, you may set the clock and the hour may not change until an hour later, even if the minute hand makes a full rotation. Now that the circuitry is done, let's put together our clock. Just move each of the rotators directly on top of one another. Then move the clock face onto the rotator. You want it as centered as possible. Now just decorate your clock. And create 2 interaction volumes. These could also be buttons, but I prefer interaction volumes. You can place these wherever you want. On my official one that I've published already, I place them on the back, like a normal clock would. Configure one of them to say reset. I would also recommend creating an interaction hold time, even if it is just a small amount. Configure the other with just set, or set clock. And to finish it off, we're going to need 3 event senders. 2 on the reset interaction volume, and 1 on the set. Wire the output of the on, use, or hold option to each of them, and continue the wiring into the next event sender for the reset. Configure the reset senders to reset and clock out. The set clock interaction volume will be set to set clock. I told you they were self-explanatory. Your clock is now complete. What's left is to start the clock. Thank you so much for joining me in the library today. Join me next time as we learn more about Rec Room.